So, welcome everybody to this webinar, which is called Volumetrics with Petrosys. We're going to show you some examples for all three types of volumetrics Petrosys deals with, and some tips that we would like you to use them when you're running volumetrics. Just please note that this webinar will be recorded and it will be available from our website in a future date. So, the agenda that we will have for today is this one. We are going to discuss some key concepts first and some type of volumetrics. Then we will have a demonstration of how to run volumetrics in Petrosys, and then we'll discuss some final points that I think it's important to share with you guys. So first, the grid-based slice is the method that we use in Petrosys to calculate volumes. It is consistent with how visual interpolation is conducted in a map view and a 3D viewer, meaning that if you display a grid in your map view or 3D viewer, and if some area is color filled, then this method guarantees that we will be calculating volumes on those areas. The grid-based slice provides a more extensive graphical analysis of the distribution of the volume within the structure by using charts and using a detailed reporting functionality, and we'll show you later how this looks in the report that we created in the volumetrics report. So first thing to note when you are going to run volumetrics, and first thing to establish is the vertical sense. Let's say, for example, that you have a grid and you're going to run volumes. Before doing anything, you have to establish the vertical sense, and we can say that there are basically two groups. One group with the positive values are going up, so we have a case where all the values for that grid are positive, above 0. Then we may have a case with some values are positive and some other are negative, and finally we have a case that all the values are negative. In all three cases, the vertical sense is positive up. In the other group, where positive is down, we have the same three cases: all values positive, another case with some values are positive and some are negative, and finally the last case with all the values are negative. So before running any volumetrics, we need to establish what type of vertical sense we're working with. Another important thing to have in mind is the cell refinement. This essentially controls the resolution of the volume computation by altering the number of times a grid cell is subdivided prior to the volume calculation. So for example, for a cell refinement of 1, it's similar to say that it's no refinement. Each subcell is centered on a grid node and has the same x, y dimensions as the original grid cell. So it will look something like this. But if we, for example, have a cell refinement of 2, then each subcell will have x and y dimensions exactly half that of the original surface grid cell, so it will be something similar to this one. So what impact this will have in the volumetrics? So let's see this slide. So when partial volumetric subcells are encountered, what Petrosys uses this percentage that we see in the slide, and it will use this percentage to calculate the volume of that volumetric cell. This can be inaccurate at times. So for example, in this particular example that we have that grid and we have an area that we would like to calculate the volumetrics on, if for example we take the cells that are cut by one corner, we have two cases. So in this particular one, if you notice, according to this table, this subcell will be contributing in a 25% of the total area. So if we notice this is small area, this doesn't look like a 25%. So in this particular scenario, we will be overestimating the volumes based on this cell size. So it's something to consider when we are choosing a cell refinement. This kind of effects or this kind of overestimating or underestimating that we may have because of choosing a wrong or a very large cell refinement or a small cell refinement. So if we keep going, we have cases where we will be contributing 50% when we cut 2 corners within the polygon, and if we cut 3 corners, then it will be 75%. And of course, the final case where we have 4 corners within that polygon, it will be contributing in a 100% basis. Another way to look at this is using the same grid and choosing different cell refinement. In this particular case, we have chosen a cell refinement of 1, meaning no refinement. I was using the original cell size. For the same grid, if we use a cell refinement of 5, then we have subcells of much smaller dimensions, meaning when we run the volumetrics, it will be more accurate because it will be based in a smaller cell size, and the possibility of overestimated or underestimated volumes, as we discussed in the previous slide, it will be less likely in this case. So cell refinement level, if we increase the cell refinement level, then we'll have a slower computation time but the higher accuracy. The opposite is true. If we decrease the cell refinement level, we will have a fast computation but a low accuracy. Another concept to talk about is the slice thickness. This controls how the volume is reported. So the finer the slice thickness, the more detailed the volumetrics report. This only impacts the computation time. The volume calculated will be exactly the same no matter the slice thickness that we use. The difference, as I mentioned, will be the control that we will have in calculating the volume. So for example, in this case, we have the same volume but different slice thickness. If we see the one with 2 meters slice, we have a better control and better understanding of how each slice is contributing to the cumulative volume. So it's a matter of better reporting and better understanding of how the volume is calculated, but the volume is the same. Another key thing to consider is whether we grid within the folds or not. If we don't grid within the folds, then no volume will be calculated in those areas. This is particularly important if we have folds with large heave. If we do grids within the folds, then we will calculate volumes in those areas. So this will be a more accurate measurement as we are considering the whole area. So the answer is yes. It's good to grid the folds because that way we guarantee that we are going to calculate volumes for the whole area. We are not going into detail on to explain how to grid within folds. I'm just going to let you know that there is a webinar in a website called Gridding with Folds. It's a very good webinar and a very detailed one, so I recommend you guys to have a look at it, so it will help you for running your volumetrics as well. So another thing to consider is whether to clip or not your grid using clipping polygons, and the answer is do not clip grids to reference planes, polygons, or zero thickness. And the reason is when you do clip your grids, you create edge artifacts, because what you're doing is removing grid nodes. So then the grid has no way of gridding in these areas, meaning that all these small white areas that we see here, the algorithm won't be able to calculate volumes for these particular areas. So do not clip the grid. The way to deal with reference levels are using reference planes in volumetrics, and I'll show you later how to do that. Another important thing is the additional parameters. So when the computed volume will be initially a gross rock volume. So this can be modified by applying scaling factors to represent average reservoir parameters. So that will be the option 1 that we see in our slide, if we consider that we have a good understanding of the field and the variability of those parameters are not that much. Then we may be able to calculate volume using average parameters. But if we have a big variability for those parameters and in that field, and if we do have those spatially varying grids that represent these values, then what you could do is multiply the grids together and use this grid as an input for volumetrics. That will be our option 2. So it depends on the amount of data and the type of geology that you have in your field. An example of how you will use these average parameters is this one that we have in the slide. We have a coal seam layer, and we have the net call for that coal seam layer, and on the top we have how to calculate volumetrics in the coal seam gas or coal bed methane. So to calculate gas in place, you will consider all those parameters that we have in the slide. So let's say that we have average parameters for that one, so we will use then to calculate the scale factor, and to finally calculate the gas in place will be net call times the scale factor. So this is to show you or to illustrate how we would use average parameters to calculate volumes in Petrosys. So type of volumetrics, we have 3 types: top and base, and thickness. The top requires a top seal grid and contact levels. The top and base requires top and base seal grids and contact levels. And thickness requires either a thickness grid, net pay, hydrocarbon pore thickness, any type of thickness layer will do. When we said reference levels, we are talking about gas oil contact, oil water contact, or zero thickness. Bonding polygons are polygons that we use to, for example, reflect the boundary of leases, or to just constrain different places. So graphically, to illustrate the type of volumetrics, we have this graph here, a map view in the top right side of the slide. We have a line X that goes from southwest to northeast, and let's say that we first have a top type of volumetrics. So we have our top grid, we have a reference level, which will be the oil water contact, and therefore and as a consequence we have 2 plays. Let's say that we restrict this even further using a base grid, and now we have constraints using this base of this formation. And if we add on top of that some bounding polygons to restrict the plays, then we will have that we are only considering the volumes for the play 1 for this particular scenario. So before going to the demo, QA/QC tip that is very helpful: always display your grid in the mapping window or 3D viewer. If you have a continuous surface, then you're calculating volumes on those areas. If there are data areas that are not color filled or white, like in this section, that it means that we won't Petrosys won't be calculating volumes on this area. So always just use your data and make sure that everything is okay. So let's go to our demo. So you launch your Petrosys. So before doing any volumetrics, always use your data in the mapping window or 3D viewer or both. So let me put this here. So I'll open this one that I have already set. So this will be the grid that we will use as input for the type of volumetric that we will run, the top one. First thing to note is that there is a continuous surface and there are no holes in our structure. Then we will need to establish the vertical sense. So these are the heights of the structures, and we see that the contours are increasing as we go down. So this means that the vertical sense is positive down. As we mentioned, we shouldn't be clipping the grids here, but we can use the color gradient to see some boundaries in or some reference planes. So if we double click in our grid layer, and let's say we establish a maximum value that we will be using later as our reference plane, and we will grid this one. And here are the two places or two prospects that we will be calculating volumes to. So just double check that the surfaces are continuous in this area, so it's all looking good. I will display two polygons that I have already prepared. So these polygons are in a sense bounding polygons. So for example, if we want to calculate volumes in just one field or the other field, we will use these polygons to select one or the other. So that's a convenient way to restrict the volumes that we are calculating. So it's all looking good in this end. So let's close this one. Let's have a look in the 3D viewer as well to see that everything makes sense from the geological point of view. So, okay, so here we have a top grid. We are using a reference plane as well, and see that everything's looking good. Notice that we have data within our fault plane, so that's good because it means that we will be calculating volumes on this area as well. So it's all looking good as well. Let's close this one. And now let's go into our surface modeling, which is the tool that will allow us to calculate the volumes. For this one, I have prepared a task for this one. Okay, so this task that I have set, I set them to grid within the folds. I'm not going to go into detail of these ones because it's not the priority for this webinar, but as I said, there is a webinar on our website that you are more than welcome to have a look at it. So let's go to Volumetrics, grid base slices, select the type of volumetrics. In this case is top, the vertical sense positive down. So let's choose the grid that we're going to use for this one. The top grid is this one, and let's go to the compute tab. Let's say that we're going to use a slice thickness of 10 meters. Look that the cell size is 10 meters, so that's pretty fine. So I guess our final level of 2 will be enough because we have then cells with subcells with dimension of 5 meters for each one of the dimensions, so that's good enough. Adjust your output volumes accordingly. Go to your polygons, choose the polygon that I show you in the mapping window. Choose both to calculate volumes in both. go to the reports tab, enable the generate reports, enable the XML report. Let's choose a name for that one. Now make sure that everything is okay. You choose a name for the report title, and we're ready to run the volumes. Let's double check. Yeah, for this particular one we're using, yeah, I forgot to mention the reference level, which I showed you in the mapping window, which represents an oil water contact. So for that interval I have set a color gradient from green to white. The scale factor, let's leave for this particular example scale factor of 1, so we'll be just calculating gross rock volume. In another example I will show you how to use the scale factor. So we are pretty much ready to run this task. We run the volumetrics, and we have our report in a HTML format that opens in your browser, and you have on the top the totals calculated. So the total volume will be in cubic meter will be this value. Then you have the totals by polygon, so it means by field. So you have the prospect in the north, the prospect in the south, and the volumes for each one of them. Then you will have a polygon by zone. In this case we only have one zone, which is the oil hydrocarbon, but if you have oil and gas, then it will be spread in those two here. And then you have the detailed report for each one of the prospects. So we have first the north one, so we have the thickness of 10 meters for each one, and the volume that is calculated in particular case. So, and we have the same information in numerical format here on the right. So we have the volume that is calculated for that slice and the cumulative volume at that particular depth. So all the information should match between the graphical and the numerical format. The same for the other prospect to the south. We have the oil water contact at the depth that we have set, and all the thickness above them, all the slices above them with a thickness of 10 meters, which is also reflected here. The area, which is based on the volume for that area, and the cumulative volume. And below that we have all the details that were considered to run this volume. So all the input data details, including name of the grid, geometry, cell size, cell refinement that it was used, the data range, the narrative of that particular grid, so how it was created, the polygon summary, units, the contact summary, and also the scale factor parameters. In this case we use a scale factor of 1, so it means that everything is 100% R1, and details about the run, when it was created. So all this information is stored here in this XML report that you can share with colleagues or supervisors, and it will be a comprehensive report that that it will be good to share as a report to anybody involved in this particular task. So let's go to the next example, which is the thickness one. I will open the DBN that I have prepared for this. So we have our thickness, our net coal for a coal seam gas field. So see that the ranges, the thickness go from 0 to 12 meters for this particular net pay example. Also notice that we are not clipping the grid at 0 thickness. We let it run, although we know that you can have a negative value in thickness, but it's better to let it run and then you clip it, or you deal with that when you're running the volumes. What else can we discuss here? Okay, notice that everything is continuous. There are no holes, so that's important to calculate volumes through the whole area. Let's say that I want to calculate the volume for a particular tenement. I have this polygon here. So this will be the permits boundary. So we'll be running the volumetrics based on this polygon here. And we will also use some additional parameters to calculate the original gas in place. So we will use average parameters, which are this one that I have annotated here. So on the top we see the formula of how to calculate gas in place in a coal seam gas or coal bed methane environment. So it involves all these parameters, and the average parameters for each one of them I have put them here. So we will use them to calculate a scale factor, and I'll show you how to use it when we run the volumetrics. So it's all looking good here. We close this one, and again launch the surface modeling. We'll launch a task that I have already set for this, which only includes when I created the grid for my net pay using data stored in an Excel spreadsheet, and then I have annotated just as a comment the scale factor. So I took all those average parameters that we saw in the mapping window, I multiplied them all together and got this scale factor, and this is the one we'll use as an input in the volumetrics. So we go again to volumetrics, grid based slices. We choose a type of volumetrics to thickness. Of course, in this case, it's not relevant the vertical sense. We choose our thickness grid, and we see how it recognizes the intervals according to the statistics. So it goes from 0 to 12.72 meters, which is the maximum net pay. The scale factor that I took from here, so we will multiply whatever is calculated times this scale factor to get the final gas in the original gas in place for this particular coal seam. If we go to the compute tab, slice thickness of 10 meters in this case, because the data range goes from 0 to 12.62. this slice thickness is too coarse, so let's say that we are going to use a 0.25 meters and a slice and cell refinement of, let's say, 5, and meaning that we will be using subcells size with a dimension of 20 meters in each dimension. The output volumes for this particular formula will be BCF, standard BCF. So it's all looking good here. Levels, polygons, we need to choose the appropriate polygon with the permit boundary. Reports, we enable the report. We change the name, let's call it OGIP, original gas in place. Let's leave it like that. We enable the XML report. We tick on the view report. Let's choose an appropriate name for this one. We're ready to run it. Click OK, and we run the volume that we have set, and here we have the report. Again, at the top, the total volume, which is 186 BCF, standard BCF. Look that it says right away the defined scale factor that we have used for this one example. Total volumes per polygons, in this case is just one, so it's the same information. And then we have the detailed graphical and numerical report using the slide thickness that we have indicated, and we have the volume that it's calculated in each slice. It looks that we will need to choose an output unit with at least one decimal to have a better understanding of how it's being calculated. That's easy to add, but for this example it will be good enough. So we have all these BCF per slice and then the cumulative BCF, so the total is 186. And at the bottom again all the input data details, the history, the narrative of the grid, the spreadsheet that I use to calculate the net pay grid, polygon summaries, and also very important the unit of the volumes. And again it tells you again the scale factor that you have used to calculate the volume for this particular example. So looking good here. Let's go to our third example. Let's open again the mapping window. So it's pretty much it's the same example that we were using for the top layer, but I have added a constraint in the base of the formation. So if we turn off the top, we'll see the base of that particular formation. So we're using the same contact levels. Notice that for this northern prospect the base is below the contact levels, so that's why we don't see any color fill. But from the southern there are some areas that are above the contact level, so that's why we are constraining the volumes with the base ones in this particular example. So it's all looking good. We can close this one. We can have a look to our 3D viewer as well. So we have the top, and if we turn it on, we have the base. Notice the grids also, the folds are also gridded, so it's all looking good, and the structure is continuous, so it all looks good from that end. We can close this one. Again, we launch the surface modeling tool, a task that I have set. I will open it. These two tasks I just created just to create the base of the formation. So I had the top, I had the thickness, and I added the thickness to the top and created the base grid from that. And now we're ready to run the volumetrics. Again, grid base slice, change the type of volumetric to top and base. The same vertical sense, it's the same scenario, positive down. We choose the relevant top and the relevant base. The levels are the same, it's the same, all water contact the same level. We use the same scale factor of 1. Compute, we need to tweak this a little bit to slice thickness of 10 meters and maybe a cell refinement of 2, because our original cell size 10 meters is already quite detailed, so there is no need to have a big refinement level in this case. And we adjust the output volumes to cubic meters, so it's looking good here. The levels are looking good. The polygons, we need to select the appropriate polygon. Reports, we just leave this title, this generic title of volume report, and select an appropriate name for the report that we are going to create. And I'll just introduce briefly this concept of display map. I'll show you what it does. So we are ready to go. We need to double check that the geometry of both grids match, otherwise the volumetric won't won't run properly. So the same cell size, same geometry, so it's all looking good. Run it. Let's wait for the calculation to take place, and then we'll show the report as well. So this will be the difference when we enable that last tab that is called map. What it creates is a visual map, and it will give you an understanding of what areas have been considered in order to create the volumetrics. So it takes a while because this refinement level of 5 meters of subcell is quite detailed. So let's wait a little bit. Okay, so this is the final report that we get. So it's the same structure as already mentioned. We have the total volumes, the volumes per polygons, and the volumes per sun, and then the detailed graphical and numerical report. So we have the north one and the base one. So notice here, for example, in the south one, how each slice is increasing until a point where it starts to decrease. This is the effect that it's created by adding a new constraint, which is the base structure. So if we don't have a base structure, then every slice, the volume calculated for each slide has to be bigger than the previous one. As soon as we incorporated a base that is above the all water contact, then it will, after getting to a maximum, it will decrease because of the fact that we have introduced a base. And that's how we know that it's actually considering the base of the formation to calculate the volumes. So we have our numeric format here with all the volumes calculated and the thickness, and again the input details. Of course, in this case we have a section for the top surface and another section for the base surface, each one with its narrative of how they were created, the polygon summary, units, and scale factors used in this particular example one. Oh yes, I forgot to show you. So this will be the map that it shows you graphically the areas that is calculating. So that's a visual assistant to see what areas have been considered in calculation of the volumes. So we can close this one. So those were the 3 examples that I have prepared for today. So let's go back to our presentation and discuss some final thoughts. So as mentioned, grid based slices is the recommended method to calculate volumes in Petrosys. It's important to establish your geological setting, and that will dictate what type of volumetrics you will run. It's important to use a sensible cell refinement in order to calculate an accurate measure of volume, so you don't overestimate or underestimate the total volume in your field. Make sure your 4 planes are gridded, otherwise volumes under these areas will be missed. Do not clip grids to reference planes, because you will create effects that will affect on your volumetrics. Use scale factor to account for average parameters, as I showed you in the thickness example. Use bounding polygons is a good practice to avoid other areas from contributing volumes. And if you require a more detailed volumetrics report, then decrease the slice thickness and you have a better control of how the volumetrics is calculated. And that's all that I have prepared for you guys today. So if you have any question, I'm happy to answer them now.